In this video, we're going to talk about just briefly the proof of how a Taylor series works. So we start with the assumption that we can represent any function with a series, an infinite series that is a polynomial. So it will start with a constant, and then of course it would have a linear piece and a parabola and a cubic and a quartic, and it's just a polynomial. Okay. Now, I just want to point out real briefly that this first part right here, this first thing, this is just the tangent line, right? A tangent line has a y-intercept, it has the initial condition, and it has a slope, x minus the x-coordinate. Now, if I plug in a to this polynomial, so f of a, so I get the first term and x minus a, well, a minus a, so this would be 0, and this would be 0, and this would be 0. So f of a would be this first term, just this constant. Now, if I found the derivative of this function, of course the derivative of a constant is gone. The derivative of this constant times x is just that constant. Here you need to see some chain rule. You bring the 2 out front, drop the power. Here you bring the 3 out front, drop the power. Again, we're doing chain rule, but the derivative of the inside is always 1. Here we drop the 4 out front, drop the power. Now, if I plugged in a to the derivative, of course, all of these terms, a minus a, a minus a, a minus a, would cancel out. So the derivative evaluated a would be this constant c1. So this is simply the function's value at a, and this is the derivative's value at a. Okay, let's keep going. So now I find the second derivative. Well, the derivative of this is 0. The derivative of this is 2 times c2. Here we bring the 2 out front, drop the power by 1. Here we bring the 3 out front, drop the power by 1. You can see I've done that. Okay. So if I plugged in a, of course, a minus a, these terms would cancel, and I'd be left with 2 times c2. So if I was solving for a constant, like the whole idea here is I'm trying to figure out what each constant represents. Well, the first constant is just the function's value at a. The second constant would be the function's derivative's value at a. The next constant would be the second derivative's value at a divided by 2. All right, well, let's keep going. Now I find the third derivative. Okay, so you can see here the pattern. This is a constant, it'll go. This will just be 2 times 3, or 6 times that. This would bring down the 2, drop the power by 1, and you can see this pattern beginning to progress. And of course, it begins to look a lot like factorial. We keep dropping a power down. So the third derivative, if we evaluated that at a, this would be gone and this would be gone. So we would just end up with 2 times 3 times c3, or 3 factorial. So to solve for the c3 constant, we would divide both sides by 3 factorial. Okay, so the first constant, let's just go back here. That very first constant was the function's value at a. The second constant was the derivative's value at a. The next constant was the second derivative's value at a, but divided by 2. And the next constant's value was the third derivative's value at a, divided by 3 factorial. Now, 2 is the same as 2 factorial. And as I said, you see this pattern. So the general pattern here is that we will find the functions, or the derivative's value at a, and divide by that derivative factorial. So like the second derivative was 2 factorial. Third derivative would be 3 factorial. So the next constant would be the fourth derivative's value at a, divided by 4 factorial. If we want to go one more, it would be the fifth derivative's value at a, divided by 5 factorial. So here's what this does for us. We said we can represent a function with a series. That's what we said. We can do this. Well, the trick, of course, is finding out the coefficients. And now we have a way to do it. To find the coefficients, we simply need to find the derivative or second derivative or third derivative, depending what coefficient we want, and divide it by the power factorial. So again, like this one would be the fourth derivative evaluated at a divided by 4 factorial. This one would be the third derivative evaluated at a divided by 3 factorial. And the way I know that is because it's always the same as the power.